So I'll focus on the specific version of FRB model, which assumes that the source is a magnetar. There are two links, just to remind you. One link is just the rates. It's not easy to come up with a source population that produces FRBs as frequently as we see. Magnetars can do that. Giant flares from magnetars can do that. The other link is the 121102, for which you can actually estimate how many particles you have in the nebula, in the persistent counterpart of the flaring object, and how strong magnetic field you have, how much energy you have in this nebula. And this was done some time ago, just from the observed luminosity. Using standard Singleton formula, you can estimate the product of the particle number of the nebula and the magnetic field. And introducing the magnetization prime to sigma, you can disentangle everything and find that the energy budget of this thing is about 10 to the 48 ergs, and the number of particles is about 10 to the 51. And this is consistent with what a flaring magnetar should do. It can produce that many particles and that much energy over its lifetime. Okay, so I'll skip this part. I hoped actually Ben would talk about it, the persistent counterpart in the nebula. So I don't think I have time to discuss that. So I'll just move on. A couple of slides on magnetar flares. I'm sure you know what they are. There are three observed real magnetars that were seen to produce giant flares. They all do the same in the sense that there is, during giant flare, they're quite similar to each other. They have 0.5 second peak and then 6-minute tail with energy budgets from 10 to the 44 to 10 to the 46 erg, which is consistent over the lifetime of this object. You infer that you have immediate 10 to the 47, 10 to the 48 erg. Okay, so the basic idea for the FRB application is that unlike the magnetars that we see, which are typically kiloyears old, if you look at the young magnetar, 30 years old, less than a century old, it can be hyperactive. And actually there is theoretical confirmation to this possibility. The hyperactivity of a young magnetar comes from very fast ambipolar diffusion in the core, which becomes sufficiently fast, meaning less than century time scale fast, if the field inside the core is about 10 to the 16 Gauss. And then this object would be producing flares like crazy, but of course not for kiloyears, only for maybe 30 years or something, maybe 1 century. We know pretty well what should be happening to first approximation such a flare. We know that most of the energy, well, some part of the energy will be emitted in the main peak, and actually it can be the brightest part of the explosion. And then there is a trapped thermalized fireball, which nicely evaporates in about 6 minutes, as was shown by Chris Thompson and Duncan many years ago. So we know what to expect approximately. The question is how you place possible FRB in this picture. It has to come ahead of the thermalization, of course, because once you have too much plasma, when it's thermalized, you cannot produce an FRB. So it has to come early enough ahead of it. Okay. Now, where can it come from? There are three possibilities that have been discussed so far. One is what was proposed by Yuri Lubarsky, who also proposed in the same paper that it can be a maser emission from a shock. Before it was known to operate in the Crab Nebula at the termination shock, the maser mechanism. But here the idea was that if you have a giant flare, it will boost the termination shock power tremendously, and it will boost it for a short time, just a millisecond time. So that would be distance scale of order of 10 to the 17 centimeters, where the determination shock of a magnetar neutron star wind is. And then you need huge power, of course, to boost it and give it high enough Lorentz factor, 10 to the 4, so you can compress the time scale at this radius, this large radius, 10 to the 17th millisecond. You need a lot of energy to produce high enough Lorentz factor to compress it. Okay, so then the possibility that I'm going to discuss in a little more detail, that you have internal shock essentially in the wind, which is driven by the magnetar flare, and then the emission occurs at a radius of 10 to the 14 centimeters. And the third possibility is that the magnetosphere itself, inside the magnetosphere, it's small radii, much less than the light cylinder, well within 10 to the 10 centimeters, or around the light cylinder, you have some kind of coherent emission mechanism. All right, so the reasons for me to focus on 10 to the 14 centimeters, because I don't think that it's easy for the radio, this intense radio wave, to get out from much smaller radius. And if I had more time, maybe I could give you some arguments, but it's an open question at this point, and it's not established yet completely what exactly are the escape conditions of for these bright radio waves. Now, two big radius are excluded because we see repeaters, and if they repeat like this at the radius 10 to the 17 centimeters, we've got too much energy, and also the recovery time of active termination shock boosted by a giant flare would be months, just because it's so big, and so you cannot repeat sooner than in a month. Okay, now what is the basic? So I think 10 to the 14 centimeters is the right kind of radius for such a burst to be produced. The basic pitch is very similar to the solar wind blast wave or shock wave. So you have persistent wind, then you have magnetic flare that ejects some energy into the wind that drives a shock. Now, in this case, we deal with relativistic wind from the Newton star in the first place, and then, of course, there is hyper-relativistic explosion. And the Lorentz factor of the blast wave, which is denoted here just by gamma, the ratio between the Lorentz factor of the blast wave material and the pre-shock wind material is given just by the pressure balance. It's like Schramm pressure balance. If you like, the ratio of powers to the 1/4 power. And so what you find in this way, for the typical flare luminosity that we think should be there, by 10 to the 47, let's say 10 to the 44 ergs ejected in 1 millisecond gives you power of 10 to the 47 ergs per second. And the wind power, it's normalized here to 10 to the 39, we'll discuss it in a second. But the dependency sees is like power of 1/4. So the ratio of blast wave Lorentz factor to the pre-shock wind Lorentz factor is 100. Now, here one should look, if you want to understand how blast wave would create an FRB, of course, in the first place, you want to understand the wind that the Newton star drives, in this case, the magnetar. And surprisingly, this problem was not actually discussed much over like decades of magnetar research. This is the canonical picture of a Newton star wind. You have a rotator, a magnetic dipole moment mu, rotating with omega, angular velocity with some misalignment. It produces striped wind, which flows away near the equatorial plane. And then you have this helical cold wind. Cold is opposite to hot here because striped wind is thought to be dissipative and it's heated up. So it's the medium there is hot. Here, this wind is helical and it's cold. And that's, I think it's the best place to produce an FRB. When something flares here and launches a blast wave, it goes through this helical cold wind, sweeps up this toroidal magnetic field that flows away from the star. And this is this gamma, which is, well, I will show in the next slide. It's about a few thousand, and this is about a few tenths gamma wind, and then it drives the FRB emission. All right. So first of all, spin down power. From normal Newton star, we know the standard formula for spin down power. If you give magnetic moment typical for magnetars, 10 to the 33 in CGS units, it corresponds to fields of 10 to the 15 Gauss. And then at the age of 10 to the 9 seconds, which is 30 years, you expect the wind, the typical wind power, spin down wind, to be about 10 to the 37 ergs per second. And it scales, the stronger is the magnetic field, the weaker is the wind power, because at the same time you have lost more rotation. Okay, now, of course, this wind is forming beyond the light cylinder. It's basically open fin lines that are wound up around the light cylinder and flow away from the star. Once you know this power, the next question that you want to understand, how much plasma there is in this wind. For that, you want to know how many pairs have been created and deposited into this wind. Now, for pulses, we think we know how to estimate it roughly. We'll take the open field line current, Goldreich-Julian current, which is written there, just equal to C times the wind power to the 1/2. And we give it some multiplicity, typically 1,000, 100, depending on the detail. So here, magnetars are dramatically different in this respect because they have a lot of current circulating in the inner magnetosphere, million times stronger currents, and they also produce pairs with significant multiplicity, 10 to the 3. So there's a lot of pair creation going on in the closed magnetosphere. And this process that creates pairs on the closed field lines, which is kind of avalanche of pair creation, in the end it shuts off, and with gamma rays that have free paths just comparable to radius, it's how it shuts off, and you produce a spray of gamma rays that are still marginally being able to convert to pairs. So in this way, you spray the entire magnetosphere with pair creation, and one can estimate, I did it in my recent paper, one can estimate how many pairs would end up in the open field line bundle from just geometry of the magnetic field. And this is how you find this outflow rate, how many pairs flow away from a magnetar with given a magnetic moment, again, field normalized to 10 to the 15 Gauss in the dipole component, and for multiplicity, which is a little uncertain, but assumed here to be about 1,000. That is, this current is producing pairs of multiplicity. For each particle carrying the current, you produce 10 to the 3 pairs. Now, these are the numbers that you should expect on average in the magnetar wind, but in fact, just before the flare, we have good reasons to believe that these numbers are significantly higher, because just before the flare, what happens during a flare? The first thing that happens, the magnetosphere inflates dramatically, so the open flux increases, and it can increase by a factor of 10 or 100, as actually as shown in direct simulations, so in this case, an axisymmetric. So just the last period of rotation to the magnetosphere becomes significantly, it increases effective dipole moment significantly. And therefore, both the wind power and the number of particles can be boosted by 1 or 2 orders of magnitude. The exact details of the exact boosting factor in luminosity and pair loading factor are not really exactly, you cannot calculate because it depends on geometry, precise geometry of the field also. But it's of this kind of order, 10 to 100. So these are the most plausible, I think, numbers for the wind power and pair loading factor just before the flare. This is the ambient medium into which the flare will go. Okay. Now we have standard theory from Michael, Goldreich-Julian papers. We know that if you have energy per particle, which you find in this case between 100 and 10 to the 4, the asymptotic wind Lorentz factor would be 3 times this eta to the 1/3. And of course, the product of the wind Lorentz factor and the magnetization, just the total energy per particle, is equal to that eta. So the bottom line is that you can have a reasonably good estimate for the pre-explosion magnetar wind parameters in terms of its Lorentz factor. It's a few tenths, and its magnetization, it's comparable to 10, maybe a few tenths. Okay, so that's one important point I wanted to make. So it's much more pair loaded than normal pulsars. Normal pulsars have much faster winds and much higher magnetization. Okay, now you launch a blast wave into this medium, and what you find is that, again, the wind Lorentz factor, we know the ratio of the blast material Lorentz factor to wind factor is 100. The shock Lorentz factor is even high because it is magnetized shock, and shock in strongly magnetized medium runs faster than the blast wave by the square root of sigma in terms of Lorentz factor. So the shock Lorentz factor is exceeding 10 to the 4. Okay. Yeah, and the blast wave begins to sweeps this wind until it reaches radius about 10 to the 14 centimeters, and it begins to decelerate. What happens in the shock wave, I leave this discussion completely to Lorenzo. He has 40-minute talk about just emission mechanisms. I think a good fraction of it will be on synchrotron maser emission. So, and Ben already described the basic picture. You have Larmor rotation, basically from a ring, it becomes unstable to bunches, and then you produce emission on that on the frequency that corresponds just to Larmor rotation in the shock. So that's this mechanism has been known for a while, and now there's 3D simulations that show rather convincingly that it does work. From these simulations and from analytical estimates, you know what is the observed frequency of this maser emission should be. It's given by this formula. It's in gigahertz range at the radius of 10 to the 14 centimeters. well, one point I wanted to emphasize here is that the emission that comes from the blast wave has to overtake the shock in order to become an FRB emission. It has to run ahead of the shock. Whatever whatever coherent emission you're trying to produce behind the shock, it gets absorbed here in this hot plasma. So the emission is beamed even in the rest frame of the blast wave. So it has to overtake the shock. In the magnetized medium, you see this additional sigma to the 1/2. It's a significant degree of beaming, which compresses the time scale even more, and which allows to get high polarization that you would normally expect. Okay, duration is written there. It's less than 1 millisecond. You take radius of 10 to the 14 centimeters, divide by gamma squared, and see that's how you estimate the duration. Your Lorentz factor gamma is so high that you get sub-millisecond duration. Radiative efficiency of this thing, Lorenzo will discuss it in more detail. This is one plot from the recent paper with Plotnikov, just numerical simulations, and then you can see that it's pretty high, 10 to the minus 5. That's just sufficient to feed many thousands of bursts using the magnetary energy budget. And polarization is linear, and the direction of polarization is set by the magnetic field and the toroidal wind, so the direction of polarization is basically set by rotation axis of the magnetar. Okay, now, and two more points. Does radio burst escape from the wind? Induced scattering, Chris already brought this up. Induced scattering is a big constraint, I think. There are two types of induced scattering. One is when you scatter waves inside the beam itself. One is when you scatter in induced way using as seeds some spontaneously scattered weak radiation. So, there is a robust constraint that kills radio signal by the induced scattering within the beam, and one can derive from, it's done in my paper, one can show that maser emission will not escape if the energy per particle in the width is less than 50. So I think that places an important constraint that the pre-shock medium should be relativistic. So that's why I'm less optimistic about the particular version of the model that Ben described in more detail. So you can imagine, so you can have internal shock in the wind itself, which is called more relativistically, or you can shock against a tail of baryonic material that expands from the Newton star and which is slow, quasi-static. So if you do this in this quasi-static material, the explosion will decelerate much faster, and it will produce, could still produce FRB, perhaps. But I'm less optimistic because I think, one, because of the induced scattering condition. In this case, you need radius of 10 to the 12 within 10 to the 13, and you also need high A prime, and I think in the end, induced scattering forbids that. And two, you cannot actually go easily into the ambient ion material in this picture, because whenever you have a magnetar with spinning down producing a wind, this ion material is always protected by the wind. There is a wind bubble behind the ion ejector. So whenever you have this wind which is polluted with baryonic material, you always inflate bubbles behind it, and when the blast wave tries to hit ion ejector, it will always hit first with the swept up wind bubble behind it, and it will decelerate dramatically before coming to the ion material. So I don't think you can easily excite strong waves in the ion material in this way. So I think it's a problem there. And also, I don't think that the sigma in this wind can be comparable to 1. It's dramatically suppressed just because this ion ejector are homologously expanding. And so flux freezing tells you that sigma is less than 10 to the minus 4. So what should be happening, and just one more minute, I think when you hit this bubble is that you produce an optical flash, because as the blast wave hits the swept up bubble, it suddenly decelerates and its coherent synchrotron power is dramatically boosted. And in that way, you can estimate the efficiency of the synchrotron emission, you can set the duration. And I think the prediction is whenever you have a frequent enough repeater, so two subsequent flares can collide between each other, then you generate optical flash with luminosity comparable to supernova 1A, and the duration will be about 1 second. And it stops being FRB at this point. And one last slide, just to advertise the work that we doing with Yuri Levin and Ashley Brunsgrove. This comes to this periodicity issue of 16-day. If you have a magnetar, you should expect it to be precessing, and you can estimate the precession period of the magnetar. And so if the deformation, which is related to how strong the magnetic field is in the star, 10 to the 16th, this roughly the deformation is about 10 to the minus 5. So if you estimate the precession rate, and you find it's about 10 to the 5, it has period of about 10 to the 5 longer than the period of the star. And the period of the star for typical magnetar is a few seconds. So you get the precession period of order of days, 2 weeks. And this is what we think what we think can explain this 16-day appearance and disappearance of the object. So if it's mildly anisotropic, I'll stop now. So it's mildly anisotropic emission. So you need it to be directed. You want to be in the solid angle of this activity. If you precess out of it, you cannot see anymore this activity. Then precess back and you see it again. Well, that's it. Thank you.
Thank you.